online lab number 3. Gravimetric analysis of arsenic. Yummy arsenic. Okay, for the so folks who have had a look at it, just by the title, I'm kind of curious. What do you, when you look at the word gravimetric, I know that my computer doesn't like it very much because when I type it out, I get this, wavy line underneath it and say, what the hell is this? It's a real word. What do you suspect gravimetric means?
Something related to gravity.
Yes, very good. Yep, something related to gravity. So in general, what does gravity do?
Keep something like in downside.
Keep something on the what side?
No, in the back, in the downside, like.
Yeah, it pulls things down, right?
Yeah.
Yeah, and that's pretty much exactly what you're going to be doing today. Is doing a reaction where something gets pulled down. One of the products of the reaction is what we call a precipitate. And we pretty much know what precipitation is, right? Precipitation is something that falls, like rain is precipitation because it falls. Well, in a chemical sense, a precipitate is also something that falls. And with a precipitation, it means that two things, we've taken two chemicals that are in solution. So they're dissolved in solution. And you mix them together and a product or products, something, one of the products of the reaction falls out. It precipitates as a solid. And that's what we're going to be doing today. We're going to be looking at, so yesterday in class, we actually learned a little bit about polyatomic anions, right? We learned that there was different elements that combine with oxygen, like phosphorus forms phosphates, and nitrogen forms nitrates. And today we're going to learn about arsenic that forms, arsenates, because we know that 8 goes on the end when an element combines with oxygen and forms a polyatomic ion. So we all know, we should know anyway, arsenic's not very good for you, right? Arsenic is a poison. It's really toxic. And so one of the ways that we can test for arsenic to see if it's present in a sample is to get the arsenic in solution somehow. So basically, I think when we look at the actual lab, the description of the lab, you'll see that what you want to do is get arsenic into solution, into like an aqueous solution. What does an aqueous solution mean? If something is in an aqueous solution, what is it dissolved in?
Water?
Yeah, water, agua. So aqueous. So if you get arsenic, like say it's in a soil sample, you would take that soil sample, you'd mix it with water, give it a good long shake in order to get all the arsenic out of or as much arsenic as you can out of the soil and into the water. So you want it to be in solution. So then that is one of your reactants in the chemical reaction you're going to do. Now the other one would be another salt. And what you're looking for is for the metal in the salt that you're adding. So remember, when you have a salt, you have two pieces. You have a salt. Of course, you have a salt. You have a salt. You have a metal that's a cation, and you have an anion, which is a non-metal. So you add that salt to the aqueous solution of arsenic, and what you want to happen is for the metal of the salt you've added to mix with the arsenate, which is the arsenic with oxygen attached to it, and that will not be non-soluble. That will not be soluble. When those two come together, then they're going to fall out of solution as a solid, and then you'll be able to measure the mass of the solid and see how much arsenic was there. Okay? So today we're going to, let me get my annotations ready. So we are going to do a couple of different things. So we're going to perform a precipitation reaction. So just like I said, we're going to have arsenic in our solution. We're going to add something to it that then causes the arsenic to fall out and form a solid on the bottom. We'll measure the mass of the solid, and from the mass of the solid, using stoichiometry. Anyone tell me what stoichiometry means? You're going to be doing a lot of it. You already have been doing some of it. Anyone know what stoichiometry is? Think way back to high school, or even further back.
It's like conversions, like making conversions.
That's a part of it. That's a part of it. Yeah, it's converting grams to moles and moles to grams. That's a part of it. There's an even more important part of it. So you're halfway home. This is the other part of it. It's the molar relationships. It's the molar relationships between reactants and products. That's what stoichiometry is. Because what we're going to do when we do this precipitation reaction, so when our arsenate containing solid falls to the bottom, we're going to have to write out what that chemical equation is. Because if we want to calculate how much arsenic was present as a reactant, we need to calculate how much arsenic is there as a product. So we're going to measure this. We're going to measure the amount of arsenic as a product because we're going to measure the mass of the precipitate. And then based on the molar relationships between reactants and products, we'll figure out how much arsenic was there at the beginning as a reactant. And so basically, this is what we call an assay. An assay is an experiment to determine the amount of something. So back in the gold rush days, when all the prospectors were heading up in north of San Francisco to like up in the Napa Valley and everything to look for gold, they would want an assay for gold, some sort of way that everyone agreed on that this is actually gold and this is the amount of gold. It would have to be some sort of chemical test to determine the precise amount of gold that somebody had. So what we're going to be doing is we're going to have a solution. Come on. I'm not able to move this. There we go. No. Why can't I? Oops. Dan. Okay. So what we're going to do is we're going to, oh man, I'm having a hard time today. We're going to have a solution that has our sample in it. We're going to have a solution that has a known concentration of the metal that will help precipitate our unknown. And our unknown is the arsenic. And then we're going to separate that constituent. That separation is going to happen by gravimetric. Gravity is going to pull that precipitate down to the bottom of our container. Then we're going to determine how much of that chemical was precipitated. And then using the molar relationship in the chemical reaction that we're going to have to balance, figure out how much was there in the first place. Okay? So there's a lot of different ways for doing this sort of assay. Good old word, assay. One is precipitation. And for precipitation, we just put an arrow next to the compound that's going to be precipitated. And here, I'm going to have to figure out some way to make this a little bit bigger for you guys to see. View. Oh, damn it. Here we go. That's a little better. So let me clear. So this is an example of an assay. If you can you see the pictures here on the left side of the screen?
Yes.
Okay. Yeah, I wish I stupidly got stuck in this sort of view, and now I can't change it. So, but you should have your, this is just taken directly from the instructions you have. So this is an assay for lead. So lead is pretty toxic too. So you've probably all heard of the Flint, Michigan, right, where the or near Detroit, where the water system was changed, and then lead started leaching into the drinking water. And so we need to be able to measure lead to a really dilute concentration, like basically parts per billion. So like very dilute samples of lead, because it's so toxic. So this is an assay for the presence of lead. So here you've got a chemical that contains lead. You dissolve it in water. So now it's in solution. So when something's in solution, the lead goes from being this to being this. And then right next to it, we put this little AQ. Anyone tell me what that means? We put the little AQ.
Aqueous.
Aqueous. So what does that mean, though?
It's dissolved in water.
Exactly. Very good. Yeah, it means it's an ion. This tells us it's an ion, and this tells us it's dissolved in water. And so it's just floating around in water. So then step 2, we add a salt-containing sulfate, also aqueous. And so when lead, +2, lead's +2. Oops, in this particular instance, lead's +2. So when we add a salt-containing sulfate in the presence of lead, we get this reaction. Let me get a different color. So we get lead 2+ aqueous plus sulfate 2- aqueous makes lead sulfate. And then this is not aqueous because it's no longer soluble in water. So we put a little brackets and S. What does the S mean?
Solid?
Yeah, it means it's a solid. It means it's no longer in solution. It's a precipitate. And chemists will put an arrow next to it to indicate that that's a precipitate because it falls to the bottom. And so here at the bottom of this sample, now we have solid lead sulfate. And so we measure the mass and determine of that lead sulfate how much of it is lead. And then based on how much of it is lead, we determine how much lead was present originally. And you can use similar sorts of assays. There's even more sensitive assays for lead where you can determine its concentration to just insanely low levels. But this is sort of one basic way that you would be able to determine how much lead is there. So one question I have for you, if I have lead plus 2 aqueous, how much, if I add, let's say, 10 times more sulfate ion than is required, is that going to change the amount of lead sulfate that is formed?
Yes.
Really? Why?
Wouldn't you have to have the same amount of lead?
Yeah, so I'm saying, let's say I had 1/100th of a mole, or as we would say, 10 millimoles. So I have 10 millimoles of lead ions in solution. Now let's say, and we know this reacts in a 1-to-1 ratio, right? So for every one lead ion, it reacts with one sulfate ion and forms one molecule of insoluble lead sulfate. So let's say I have 10 millimoles of my lead sulfate, and I add 1,000 millimoles of sulfate. Am I going to get more lead sulfate precipitating or the same amount?
The same amount?
That's right. That's right. You're going to get the same amount because we say that the lead is limiting. That is a limiting reactant. And then we're going to get into this more later. But a limiting reactant basically means what it says. It limits the amount of product you can get. And the sulfur, the sulfate, is in excess. So basically that means we can add as much sulfate as we want. We can add more and more and more and more and more. We're not going to get any more precipitate because it's limited by the amount of lead. So if you're doing this sort of experiment, what you need to do, and then that's one of the things you're going to be doing yourself when you do the experiment, is if you need to add a little more, a little more, a little more. You have to add a little more sulfate because you don't know how much lead is in there. For instance, in our experiment, we won't know how much arsenate is present. We don't know, so we're going to add a little bit of, and in our instance, it's silver we're going to be adding because silver arsenate isn't soluble. So we're going to add a little bit of silver, measure how much precipitate forms. We're going to add a little bit more, see how much precipitate forms, and add a little bit more and see how much precipitate forms. And at some point, it won't matter how much more silver you add. You won't get any more. You won't get any more precipitate. But we need to go beyond the amount required to ensure that we precipitate all of the arsenate. Okay, so we'll try a little bit and see what we get, and we'll try a little bit more and then see what we get, because we want to make sure that the thing we're measuring, the lead or the arsenate or whatever it is limiting. We want to make sure that all of it gets consumed in the reaction so we can measure it. And it doesn't really matter if we have an excess of the other, because the excess, what happens to the excess in this instance? What do you think happens to the excess sulfate? So if we have excess sulfate in the solution, what happens to it?
In extra?
Yeah, so we have extra sulfate. What happens to it? Does it precipitate? Does it just hang out? What does it do? So we've got sulfate that's aqueous. So we've got sulfate ions in solution. What happens to the excess sulfate ions that are in solution?
Nothing?
Nothing. That's right. Nothing happens to it. It just stays in solution. That's what it was doing anyway. And so there's no more lead for it to interact with, to react with, and precipitate. So nothing happens to it. It just stays in solution. So you just have a solution of sulfate. That's it. Because remember, when you add salt to water, you just get sodium ions and chloride ions, and they're just swimming around. They're not interacting with each other. They're interacting with water now. They're ions in solution. So they don't actually do anything with
That's
each
mean
other.
the solvate is soluble?
Yes, they're soluble. They're solvated. Yes, and we're going to get into what that means a little bit later. But yeah, if it's in solution, that means it's been solvated by the water. And we'll talk. That's near the end of the term. I'm going to talk a lot about water, but yeah, water does the interacting with the ions. All right, so let me clear that, and let's go to the website if I can. Okay, here we go. Can everyone see the screen okay? Let's see if I can change the sharing. Man. Okay, so here's the screen. So gravimetric determination of arsenic. So when you click on the title, it gives you a rundown of basically why we're doing the experiment. And so you can see that arsenic in history it's been known about for a really long time. It's been known to be toxic, but it's still a problem today. So the biggest problem being the presence of arsenic in drinking water in wells. So you want to be able to see where the arsenic's coming from. So in this particular example, we're going to look for the concentration of arsenic in 2 samples of contaminated soil. So, and this is the form of the arsenic we're going to be looking at, arsenate ion. So just like phosphate, so we know that phosphate is PO4, right? This is phosphate, PO4 3-. And so it's probably not surprising that since arsenic is just below phosphate in the periodic table, that arsenic, when it forms an ion with oxygen, forms arsenate. That's also -3. It's just another example of the periodicity of chemicals on the elements in the periodic table. If one element forms an ion with 4 moles of oxygen with a -3 charge, the one below it probably going to form the same thing, and that's true here. So just like phosphate, we have arsenate, and this is the reaction we're going to be doing today. We're going to be taking arsenate soluble, so that's going to be a soluble arsenate ion in aqueous solution, so it's going to be in water. We're going to be adding a salt that contains silver. And so when silver ions and arsenate ions come together, they react and they form silver arsenate. And you can see that there's an S here, and now we know that S means solid, and it precipitates. So if you want to measure the concentration of arsenate in the solution, what we're going to do is measure the amount of product that's formed, and then go back and figure out how much arsenate must have been there in the first place. Okay, any questions about that so far? I know I've sort of been blathering quite a lot. Are there any questions? This is like a classic chemistry experiment that we do. We do these experiments are done like all the time to test for like a variety of ions in water. Basically, take something that's soluble, turn it into something that's insoluble, and then you can measure it. But
Just, I have, I know is earlier a question, but just I want to know which method we gonna measure this product, and like how we can measure.
we're going to measure the mass. We're going to measure the mass of the product that precipitates. Yeah, that's all we're going to do. Just so we're going to do the reaction. We're going to add a solution to another solution. So everything's in solution. Everything's soluble. Everything's ionic. Everything's a solvated ion in solution. And then when two of those ions come together, in this instance, arsenate and silver, when they come together, they're going to form a solid which falls out of solution. And we're just going to measure the mass of the solid. Okay? Is that clear?
Mm-hmm.
Okay. So one thing I wanted to get into before we start is something we haven't talked about yet. And that is molarity. There's going to be something you haven't talked about yet, you're not familiar with yet, and that is capital M. You're going to see a solution, and it's going to say something like, this solution is 1.00 capital M. Does anyone know what that means?
Mm-hmm.
This is a measure of molarity. Anyone know what molarity is? Oh, so it's going to be a learning experience for everybody today, it sounds like. Okay. Nobody wants to take a guess. You're free to take a guess. Remember, I don't yell at people for having the wrong answer. I will yell if nobody says anything. Just take a stab at it.
Wait, is it how much of a ratio of a mole it is?
Yeah, it's a ratio of a mole to what? What's it a ratio of? Yes, it's moles per something.
Either mass or density.
Nope, but it's moles divided by something.
Is it liters?
Yes, there you go. Moles over liters. Now, the reason we have to have this is because so far we've been converting mass to moles, right? And we're going to keep doing it. But then, so the reason we can do that is because with mass, we have a solid. We can measure the mass of a solid. That's easy. Just put it on the balance. You measure the mass. You get grams. You convert grams to moles. Everything's good, right? But what do you do if you have a solution? It's much harder to measure the mass of well, you can measure the mass of a solution, but it's also got water in it. It may have a whole bunch of other stuff in it. You don't know how much of the thing you want to measure is in there as part of the mass of that solution. So what we do is instead of measuring grams and converting it into moles, we measure the concentration. And so the concentration is in moles per liter. And we call that capital M molarity. So a solution that has 1.00 molar. So we say molar, that's what this is, just like a tooth, molar. That means it has 1 mole in 1 liter. So we can use that to measure moles when we have solutions. So it's actually easier than when it's a mass, because we don't have to convert grams to moles. That's been done for us already. We're just going right from liters right into moles. And we don't use grams per liter because we're not interested in grams, right? We're interested in moles. We want to know moles are the unit that chemists use that react with each other. Grams don't. Moles interact with each other. Grams don't interact with each other. So we already take care of that and measure the concentration in moles per liter. Yes, Erica.
Would molar mass be a completely different thing?
No, we would use the molar mass. Let me clear this out. So let's say the mass of sodium chloride. So sodium's like 23 and chlorine's like 35. So it's around 58 or so, 58 grams per mole. So that means if I dissolve 58 grams of sodium chloride in 1 liter of water, I have a 1 molar solution. Okay. It also means that I have a 1 molar solution of sodium ions, and I also have a 1 molar solution of chloride ions. So basically I have a 2 molar solution of ions total. So it just means that the mass of 1 mole is dissolved in a liter of water. So we still use the molar mass is still essential. And so if you want to, so what we're going to do, if you want to go backwards and calculate how many grams, let's say we're going to calculate how many grams of arsenate is present, we're going to have to figure out how many moles of arsenate were there, and then use the molar mass to figure out how many grams. So yeah, we still need to know the molar mass of things. But when we're in solution, when we have a solution of something, that's we're interested in the moles per liter concentration, not so much the grams per liter. Because when we do, this is for, another thing to point out, this is for reactions in solutions. So if I have a 1 molar solution of A and a 2 molar solution of B, and my reaction is A plus B gives C, what that tells me is that I'm going to need twice as much A. I'm going to need 2 liters of A to mix with 1 liter of B to get my reaction, because this one is twice as concentrated. So I'll need twice the amount of A to make that reaction go. If I had these concentrations in grams per liter, I'd have no idea how much I would need. That wouldn't tell me anything. I would need to figure out how many moles of each one in order to make this work. Is that clear to everybody? Because we're doing reactions in solution, and so we need to know how many moles of each one. Grams aren't going to help us. We need to know moles, because that's what interacts. That's what forms reactions. Grams don't. Moles do. Is that clear to everybody?
Yes.
Okay. So this is the reaction we're going to be doing. So we're going to have arsenate in solution, right? So we're going to have a certain amount of that in solution. And what we're going to be doing is we're going to be adding a solution of silver nitrate. So silver has, everyone remember what the charge on silver is? Silver is one of the exceptions. Silver is always the same charge.
Do you want us to write this down?
Unless you could remember it all. Yeah, I'd be writing this stuff down if I were you.
Is that AG or AS?
AS is arsenic and AG is silver.
Oh, okay. So
Yeah.
AS.
So our reaction is arsenate. This is the reaction you're actually going to be doing. Arsenate ion plus silver nitrate. So what's the charge on silver? Anyone remember what that was?
2 plus.
Excuse me?
2 plus.
Nope. Remember, there's like silver, and then as you go up, there's zinc, and then you go up one more, and it's aluminum. Aluminum is +3, zinc is +2, and silver is
+1.
+1. Right, so silver's +1, which means that what must nitrate be? What must be the charge on nitrate? This is the nitrate ion. What must be the charge on it?
-1?
That's right, it has to be -1 because there's a 1-to-1 ratio. If there's only one silver and there's only one nitrate ion. Nitrate is another polyatomic ion, and it has a charge of -1. So these are going to be the ions in solution. Then the reaction's going to form, and a precipitate is going to appear. That's going to be the solid. The solid is going to be silver arsenate. And nitrate is going to be left over. Aqueous. Now the question is this a balanced reaction?
No.
No, there's a problem with this, isn't there? Is that the right formula for silver arsenate?
It's AG3.
Yes, it is. Very good. There's a 3 here because it takes 3 silver ions to interact with 1 arsenate ion, because there's -3 and silver's +1. So you need 3 silvers to interact with arsenate. So this is your solid, and it precipitates out. So now is our reaction balanced? Because we have to have a balanced reaction before we can do any calculations.
You need to
Couldn't hear you. What was that?
on the reactant.
Man, I really can't hear you.
Wouldn't you need to balance the silver on the reactant?
Yes, you do. How are we going to do that? You need to balance the silver. She's right. The silver isn't balanced. We have 3 moles of it as a product, but we only have 1 as a reactant. So how are we going to balance that?
Put 3 in front of the
In front of what?
silver.
Where?
Oh no, you can't change. Can you change the reactant?
Sure, we can change the reactant, definitely. Where am I going to put the 3 though?
In front of the silver?
Just the silver? I can't change the reactant. I can't put a 3 there because that's not the formula for silver nitrate. So where am I going to put my 3?
On the front of the silver nitrate.
In front of the silver nitrate, exactly. I'm going to put it here, which means I need 3 moles of silver nitrate to react with 1 mole of arsenate ion. Okay? So is my reaction balanced now?
Yes. NO3 for NO3.
That's right. Yes, 3 here as well.
Gonna be, I think, yeah.
Yeah, so we'll learn later on that when you do this sort of reaction, there's something called a spectator ion. Because since this is aqueous, silver nitrate is aqueous, basically what we have is silver ions and we have nitrate ions just floating around doing their thing, right? They're not interacting, they're interacting with water. And so there's going to be 3 moles of silver nitrate ions at the beginning of the reaction, and guess what? There's going to be 3 moles of silver nitrate ions at the end of the reaction. They're going to do bupkis. They're not going to do anything. So so we call these spectator ions because they're basically a spectators to what's going on. They were there at the beginning, they're there at the end. They didn't do anything. So what our net reaction is, the things that actually occur, our net reaction is this plus this make this. And the nitrate ions don't really play a part in the reaction. They're just floating around at the beginning. They're going to be floating around at the end. So our net reaction is 1 mole of arsenate ion plus 3, oops. What happened to that? Plus 3 moles of silver ions give us 1 mole of silver arsenate solid, okay? So we're going to leave that up so everyone can have a chance to have a look at it. Okay. All right. So is that clear to everybody? That's what our reaction is going to be. So let me erase some of this just to make it really clear the reaction that we're doing. So we're going to be measuring. This is our reaction. Arsenate, aqueous, minus 3, plus 3 moles silver ions, plus 1, give 1 AgAsO4 solid precipitate. This is what we call the net ionic reaction, because this ion and 3 moles of that ion make our product. So we call that the net ionic equation, because everything else was there at the beginning and it's going to be there at the end. Like for instance, the arsenate ion is probably there in the presence of sodium or something like that. It's probably a sodium 3 arsenate. But as soon as that goes into solution, the sodium becomes ionic and sort of floats away. So we get 3 moles, oh damn it, we get 3 moles of sodium ions. So we get 3 moles of, oh god damn it, 3 moles of sodium ions, which are going to be there at the beginning of the reaction and they're going to be there at the end of the reaction. So at the end, we're going to have sodium, 3 moles of sodium ions, and 3 moles of nitrate ions. We're going to have sodium nitrate, and that's all in solution. Okay, so let's go back to, oh man.
Question, what happened
Yeah.
to the silver nitrate?
The silver nitrate, right. So silver nitrate is in solution, meaning that, let me pull up let me get another whiteboard up here. Clear everything. So when I get having a hard time with this thing today. I want to draw in, let's do purple. So if I have, let's say I have a 1 molar solution of silver nitrate. So I'll reach for a bottle, and this is what it'll say on it. It'll say 1 bottle, it'll say 1 molar silver nitrate. What that means is that in that solution, I'm going to have silver ions and I'm going to have nitrate ions. And they're both aqueous, right? They're both in solution. So they're not interacting with each other anymore. It just means that silver's floating around by itself and nitrate's floating around by itself. So that's what 1 molar silver nitrate means. It means if something's is given a molarity, it means it's in solution. It means if it's a ionic compound, it means it's now ions in solution, no longer stuck to each other. Because I took solid, this is an actual reaction. I took solid silver nitrate, I added water, and this is what I got. I got that, and I got that. That's an actual chemical reaction. So I don't have solid silver nitrate anymore. I have this, and I have this. So that's what that means. So what's going to happen is that the reaction that we're going to do, the silver is going to be in the reaction, and the nitrate is going to do nothing. We're only interested in the silver. The nitrate's not going to do anything. Is that clear? Okay.
Yes.
All right, cool. All right, so let's share the screen again. All right, so here's our workbench. And we're going to do a couple of test reactions first before you go and try and figure out how much arsenate is in unknown samples. So I think in the procedure, we're going to select, so we go to solutions. Can everyone see, can everyone see the workbench of the website? Can everyone see this? See the little hand on the solutions?
Yes.
Okay. All right, so we'll go to solutions and we'll select sodium arsenate and put that. So 0.01 molar sodium arsenate means that in 1 mole, in 1 liter of this solution, there is 0.01 moles of sodium arsenate. Okay? Where is my annotate? So what that means basically is that in this solution, I'm going to have 0.01 molar arsenate. I should probably pick a different color because that's hard to see. So I'll have 0.01 molar arsenate. What's going to be my concentration of sodium? Is it going to be the same or different?
The same.
Okay. Anybody else want to hazard a guess?
Would it be 0.03?
Yeah, actually, that's right. It'll be 3 times more because in solid sodium arsenate, there's 3 moles of sodium ions for every 1 mole of arsenate because arsenate's -3, right? So there needs to be 3 times as much sodium in order to balance that charge. So when I put it in solution, and remember, molarity means solution. It means all of it is in solution. So when it goes into solution, they separate. And so for every 1 mole of arsenate that goes in solution, there has to be 3 moles of sodium ions. for the charge to balance. And so my concentration of sodium is 3 times as much. Sodium. Okay. Now, luckily, we don't really care about the concentration of sodium because, like I said before, it's a spectator ion. It's not going to do anything. It's going to be there at the beginning of the reaction. These sodium ions are going to be floating around in solution after we add before we add silver, and they're going to be floating around after we add the silver. They're not going to do anything.
Just a quick question. How
Yeah.
do you use the material Na3ASO4 from the website? Like how you choose the volume, how you choose the solution from the mutation? I don't know.
Oh, that's just the solution that's given. That's the concentration that's given. It's dilute. Because we're going to be working with dilute solutions
Yeah,
of arsenate.
How I can get it in the website? Or it's automated, it will come. Do I need to click in any item?
Oh, you don't know how to get it?
Yeah.
Oh, go back to the stock room.
Mm-hmm.
Click on solutions. And it's the third one there. So if you just click on it, it appears on the bench. So there's our solution of sodium arsenate.
Ah, okay, got you.
Got it? Okay.
Yeah, thank you.
All right, so we're going to have different concentration of sodium and arsenate. So just to be aware of, because it will be involved when we do our calculations later. So next thing we want is their silver nitrate. So here's our solution of silver nitrate. Now, I'm going to go back to the stock room, and I'm going to get something to pour both of these things in. So I'm going to go down, click on glassware, beakers, and a 250 ml beaker or a 600 ml beaker, doesn't really matter which one. 250. Okay. So what I'm going to do is pour all of the arsenate into the beaker. And so to do that, we hover over the arsenate, we click on it, and drag it to the beaker. And then when it's over the beaker, and when you let go of the mouse or the whatever you're using, the touchpad, you'll be able to type in exactly how much you want to add. So I'm going to say the whole thing, 100, and then pour. Pour. Uh-oh, hope this doesn't mean we're going to crash. Come on. There it goes. Yeah, so you can see that now it has 100 mils. I'm going to put that back over there. So now if you click on the 100 ml beaker, it'll tell you it has 100 mils in it. So here's so it has 100 mils of solution in it, okay? And grams, none, because nothing's precipitated yet. But now we need to do a calculation. Whoops. We need to figure out how much of this silver nitrate are we going to have to add to this to precipitate all of the arsenate. Okay, that's something we're going to need to calculate. So I have 100 milliliters of 0.1 molar arsenate in solution, right? I have 100 mils of 0.1 molar arsenate. How many moles is that? How are we going to how do we figure out how many moles that is? So what's the number of moles? How do we calculate it? Moles of arsenate.
Do we divide 0.01 moles of arsenate over 100 ml of water?
Nope. Remember, I don't want you to, never want you to divide anything. Always multiply with units, because then you can see whether you've done the conversion properly. So what I would suggest is we convert this to units we can use. Now, anyone remember what molar means? What does that mean?
1 mole over 1 liter.
Right. It means 1 mole over 1 liter. So how do we so if we express 0.01 molar, that would be equal to 0.01 moles over 1 liter, right? That's what that means. That's the actual meaning of capital M. So that's what that means. So what am I going to multiply that by so that at the end I get moles? What do I multiply this by to get moles out?
1 liter over the moles of the molar mass of arsenic.
No, I'm just going to want to multiply that by something so I can cancel out liters and leave me with moles.
1 over 1,000.
That's just a number, though. I need something with units in it.
1 mole over 1,000 liters.
So if I multiply that by moles over liters, my units are going to be moles squared over liters squared. That doesn't make any sense. I need to multiply by something that cancels out liters and just leaves me with moles.
1 liter over 1 mole.
1 liter over what?
1 mole.
Oh,
No, again, if I, where does that come from though? If I multiply that by 1 liter over 1 mole, then I'll just have a unitless number. Remember, I need to be left with moles at the end. I'll give you a hint. It involves this number.
1 liter over 1,000 milliliters.
Then that's just volume over volume, and I'll still be left with, so that would be a unitless number, volume over volume, and I'll still be left with moles over liters. I need to multiply this by something that basically has liters in the numerator and nothing in the denominator, so that when I multiply by it, I just am left with moles. What number am I going to?
by 1 liter.
Why am I going to multiply it by 1 liter? Where's the 1 liter coming from? I haven't got 1 liter. I've got 100 mils. I'm not adding a liter of this. I'm only adding 100 mils of this.
0.1 liter.
There you go. Over nothing. Over nothing. You just multiply it by the volume. And the volume we're adding is this. This is the concentration of arsenate, right? This is our concentration of ASO4 minus 3. This is our concentration right here. So we need to multiply it by the volume of our arsenate. And the volume is 100 mils. And 100 mils is 0.1 liters, because there is 1,000 mils in a liter. So 100 mils times 1 liter over 1,000 mils equals 0.1 liters. So this is what we want to use. So when I multiply 0.01 moles per liter times 0.1 liters, how many moles do I get?
.001 moles.
Right, I get 0.001 moles of arsenate. ASO4 minus 3. That's how many moles I'm going to get. Now, we need to calculate what volume of silver nitrate do we need to add in order to react with this much arsenate. Now remember, we have to go back to our original reaction, and the original reaction was
Isn't it 3 times?
you're way ahead of me. Excellent. Why 3 times as much?
Because it's a 3-to-1 ratio.
That's right. So that means since there's 3 moles of silver for every 1 mole of arsenate in our reaction, we're going times this, we're going to need 0.003 moles of silver. So now we need to go backwards and figure out what's the volume we're going to need. So let me just clear all this. So we have 0.003 moles of silver, and the concentration of silver we have is 1.0 moles of silver per liter. Now the question is, how many liters? I need to have liters of silver nitrate. How am I going to get that? Equals 0.003 moles times what? Now I want to multiply that by something so I get liters at the end and get rid of moles. So I have moles, and I want to convert that to liters. Now to do that, I'm going to use
0.001 moles over 0.1 liters.
Where am I getting 0.01 from? That's the concentration of the arsenate. That's not the concentration of the silver. This is the concentration of the silver. It's 1 molar. It's a much higher concentration. So I need to use the concentration of the silver nitrate, because remember, concentration is the relationship between moles and liters. I have moles and I want liters, so I'm going to use the concentration to get me there. So what am I going to multiply moles by to get me liters?
1 mole of Ag over 1 liter.
Nope, because that's going to give me moles squared over liters squared.
It would be 1 liter over 1 mole of.
There you go. Yes, 1 liter over 1 mole. That's the concentration, right? That's the concentration of the silver, 1 mole over 1 liter. We just flip it upside down and put 1 liters on top and moles on the bottom. It's still equal. There's 1 mole in 1 liter, and in 1 liter there's 1 mole. It's the same thing. But we need to get rid of moles, and we're left with liters. So how many liters is that?
Liters.
Yeah, 0.003 liters. That's right. How many milliliters is that? Because really, you see, we're measuring things in milliliters. Milliliters here.
3 milliliter.
How many?
3 milliliter.
3, that's right. Because we moved, there's 1,000 milliliters in 1 liter. 1, 2, 3. So we moved this decimal 3 places. 1, 2, 3, 3. So 0.003 liters is equal to 3 milliliters. So we need to add 3 milliliters of this 1 molar solution of silver in order to precipitate all of the arsenate. Okay, is that clear to everybody how we did that? Because it's a 3-to-1 ratio. We need 3 moles of silver for every 1 mole of arsenate.
Yes, it's clear.
That's good for everybody? Now, I'm recording this, so you can always go over it again later. So let's actually do the reaction. I'm excited. So let's clear everything. Now we can do the reaction. So here's my beaker. It's got the arsenate in it. Now let's come on. Now for grins and giggles, let's add 2 mils and see what happens. So I'm going to drag it over. And it says, how much do you want to add? I'm going to put 2 mils. And pour. Now, see how many, this tells you, I'll go back up here. This tells you how many grams of precipitate were formed, which is kind of nice. We don't even need to measure it. It measures it for us. So that is the amount of solid that was formed, and this is the precipitate. So that is the silver arsenate. Solid, that's the reaction that we just did. And this is the amount of precipitate. The question is that all of it? So when you're doing your unknowns, this is what you're going to be doing. So you're going to measure the amount of the precipitate, then you're going to add a little more, then you're going to add a little more. And when this stops, when the amount of precipitate stops increasing, then you're done. Basically what that means is that you have titrated, that's another word we'll learn about more later. You basically have reacted all of the arsenate. It means you can't make any more silver arsenate because all the arsenate ion is gone. And once all the arsenate ion is gone, you're not going to make any more product. No matter how much, you could add this whole thing of silver and you're not making any more, okay? So let's add another little bit and see if we get an increase. The other thing you could do is, since the molar mass of silver arsenate is, the molar mass of silver arsenate is 462.52 grams per mole. So if we actually had 0.001 moles of arsenate, what's the mass of arsenate we would expect to see? So this is the mass of silver arsenate. If we had this much silver arsenate, what's the mass of solid we would expect to see? What is it?
0.46252.
That's right. If all of the arsenate was converted to this, we would expect to see that much precipitate, but we don't, right? We see less. So let's add some more silver. What this means here with, because we have 0.3 grams, it means we still have arsenate ion in solution because we haven't we haven't got this total yet. So let's add some more and see what happens. So I'm going to take my silver arsenate over. I'm going to put it over the solution again. And I'm going to add another 1 mil, 1.0. I'm going to add another mil. Okay. Now, click on the beaker and look at the mass of the precipitate. Kind of looks familiar, right? It's pretty much exactly what we expected if we precipitated all of the arsenate and converted it into silver arsenate. So we predicted we would have, oops. We predicted we would have 0.4625, and we have 0.4625, basically. So that means we've precipitated all of our arsenate by converting it to silver arsenate, which is a solid. Now, I'm going to add some more silver arsenate. I'm going to add another 10 mils. What do you think is going to happen to the volume, to the mass of the precipitate? Is it going to go up some more? I mean, I'm adding more silver.
The volume will go up.
I'm sorry?
The volume will go up.
It'll go up?
Yes.
By how much? I mean, I'm adding a lot, so it must be, do you think it's going to go up a lot then, huh?
Not a lot. Probably 10.
Up by a factor of 10? So I've added 3 mils so far. If I add 10, that means it'll go up by a factor of 3. So I'll get like around 1.2 grams.
No, like probably around 15 milliliters.
15 grams?
15 milliliters.
No, I'm adding 10 milliliters of silver. The question is, am I going to get any more precipitate product? Yeah, I mean, the volume will be more, but will I get any more precipitation product?
No.
No.
No. People seem to think no. Well, let's try it. This will prove it, right, to see if we get any more. So I'm going to add 10. And let's have a look. So in our beaker, our volume is more than it was. It's gone up another 10 mils, not surprisingly. And our mass of our precipitate has not increased. It's the same as it was, 0.4625. So basically what that means is that the silver ions and the nitrate ions are now just in here. They're just, oops, let me go back. So the silver ions and the nitrate ions are now in this beaker, just floating around. So there's silver is there. It's just an ion floating around because there's nothing that's there for it to react with that will cause it to precipitate. All the stuff that would have made it precipitate is gone. So now it's just chilling, floating in solution. And the nitrate wasn't doing anything anyway. It never was. It's a spectator ion. So we could add we could add the whole darn thing if we wanted to, and the mass is not going to increase. So what we would do in that instance, if this was our unknown, we would write down the mass of our precipitate, and we would use the molar mass of silver arsenate, 462.5, and then figure out how many moles we had. Okay, so what you're going to do is the same thing. Now it's going to be unknowns. So you're not going to know how much silver to add. So you're going to have to try a couple different volumes. And when they stop increasing, you'll know that you've made all of it. So I'm just going to sort of do one without the calculations. You're going to have to do the calculations. So let's get all this stuff off the, so remove, I guess we can leave that here and remove that. Remove. So go back to the stockroom, click on solutions and go sample 1. And it's up to you to decide, oh, and let's pick out something to put it in. Stockroom, glassware, beakers, there we go. So sample 1, you can put in, let's put in 50 mils. So I'm going to transfer 50 mils. Put my sample 1 over here. And then I'm going to add some, so I don't know what the concentration of arsenate is in here. I have no idea. So what I'm going to do is come over here, add my 1 molar silver nitrate. I'm going to add, let's say half a 0.5 mils. Click on the beaker again. Okay, so what that tells me is that I have produced 0.077086 grams of solid. So there is some arsenate present in the solution, and we've turned it into silver arsenate and precipitated some of it. I don't know if we precipitated all of it, so we would add some more. So let's come back, go to the mouse, and add some more. Let's add another 0.5 mils. And, oh, twice as much. That makes sense. Now we've got 0.154 grams. And basically you just keep doing that and keep doing that, adding a little bit, until all of it has been, till the mass of the precipitate does not increase anymore. Then you're going to figure out how many, you're going to take the grams of silver arsenate, and you're going to convert the grams to moles. Okay? Figure out how many moles of arsenate there is. And then I think at the end, you are going to figure out what the mass percentage is, arsenate in the solution, in that sample. So you're going to want to figure out what's the mass of the arsenate in the solution and divide it by the mass of the solution. And so you can do that using the density. So the density of the solution is given as 1.05 mgs per mil. So you could use that density to figure out what the mass of your density is. So in other words, if you had 100 mils of solution, the mass of it would be 105 grams. So 105 grams is the total mass of the solution. You figure out how much of that mass is just arsenate by itself and calculate the percent mass. So is there any questions about how to do that? You're going to be doing a lot of conversions of grams to moles and moles back to grams.
So how you get to that icon information?
Which icon information?
Here.
Oh, here? Let me, that information?
Yeah.
Oh, just click on the beaker. So look here, let me get the, so if I click on the sample, let me just clear everything. There's a lot of stuff here. So if I click on the sample, it tells me what's in the sample. So here, It's telling me I have 50 mils of sample 1 in that container. Now if I
But
click,
in my icon, I do not have 50.000 ml. How can I change it? I have just sample 1, 0.1. How you get?
that's a different sample. That's a different sample. So go back to solutions
Mhm.
and scroll down to sample 1.
Yeah, my sample 1 is just 0. Yeah, this is okay.
It shouldn't have any concentration on it because it's unknown.
Okay. So I click on sample 1.
And it appears on the, and then when we click on it, it says there's 100 mils of sample 1 in there.
Yeah. Okay.
Okay. And if we click on the 1 molar silver nitrate, it'll tell us what's in it, 1 molar silver nitrate, and how much volume is left. And then if we click on the beaker, it'll give us the volume we've added to the beaker so far. And if there's any precipitate in there, it'll tell us how much precipitate's in there and what the precipitate is.
Okay.
So basically, we're just going to keep adding silver nitrate to the beaker. Come on. There we go. And just keep adding more volume until that mass of the precipitate no longer increases. And then we know we've precipitated all of the arsenate in that solution. It's all gone.
Okay, can you show me how can I add silver?
Oh, sure. So let me get rid of this. So we just click on the silver nitrate and drag it over on top of the beaker.
Do we always start with 50 milliliters of the sample?
Oh dear, the internet connection is becoming unstable. Oh good. So I'm going to drag it over there. So then you see volume. You have a little flashing, click on the volume in here and say I want to add, say 5 mils, say 5.0 mils, and then click on pour, and it will pour it in for you. Okay, and then just click on the X to get rid of it. It'll say 5.00 mils transferred. And then my computer's going to crash. Come on. There we go. There we go. So then we click on the beaker, and we can see that we now have more. We have a higher amount. We have a higher amount of solid precipitate now. So we just keep adding and adding and adding more and more volume until that number no longer increases. And then we've precipitated all of the arsenate from our sample number 1.
I have a question. How do you know to start off with 50 milliliters?
You can use whatever volume you want. You can use 20, you can use 50, you can use the whole thing. You can use 100 if you want. It doesn't really matter. If you use less sample 1, you'll need less 1 molar silver to precipitate it. That's all. In fact, 100 might be easier because it makes your calculations easier.
And then my other question is, how did you get the density as 1.05?
Oh, that's in the instructions.
Oh, okay.
Yeah, that's in your instructions. So, can you see the instructions here?
Yeah, my printout doesn't print in ink. It's kind of hard to see.
Oh, you can you can just look at it online, or just download the PDF and look at that.
Okay.
And it's got, Yeah, so here's your sample. So you can use 100. It's even suggests using 100 mils. Use whatever you like, and just keep adding it till you finish precipitating all of it. And then the question is, what's the how many moles? Let me draw on this. So how many moles? So this is the mass of your precipitate. So the first column here is what's the mass of the precipitate you got? From that, how many moles of arsenate were there? And then from that, how many grams of arsenate was there? And then from that, from the original solution, what's the mass percentage of arsenate? And so you need to assume, so in order to calculate the mass of your solution, you need to know what the density is. Because all you know is that you used 100 mils of solution, or 50 mils, or however much you used. And you need to convert that to grams. And so to do that, you need to have the density, because that's the relationship between grams and volume, right? Between mass and volume. So you then just convert however much volume you used to grams, and then you take the mass of the arsenate and divide it by the total mass of the solution. And then that gives you the mass percentage, percent mass. Oh, I'll multiply it by 100, of course, since it's a percent. Okay. Yeah, so it's in the instructions.
For the data table, it shows 2 sample ones and 2 sample twos. So are we supposed to do it twice or?
You can do it as many times as you like. Yeah, you should do it at least twice.
Okay.
Yeah. You want to do it at least twice and make sure you get the same answer both times. You should get the same mass of sample each time.
And for volume, we like input into our data table the volume that when we reach like the precipitation, like that volume.
No.
Oh, okay.
No, you want the original volume. So
Okay.
yeah, you want the original volume that you use. So you use this volume. When you're calculating the mass percent, you just want the mass percent of arsenate that was present in the original sample. So if you use 50 mils of sample 1, you just calculate it using 50 mils. You wouldn't use it. You wouldn't say 50 plus. Let's say it was 75. If you added another 0.75 mils of silver to precipitate it all, don't use this. You use the original.
Got it.
Yeah. Because
So if I put
because the additional stuff you added had no arsenate at all in it, so it just had the silver. Yeah, another question.
So if I say that I started with 0.5 mil, I'll just put 0.5 mil.
Yeah, if that's how much you start it with. I don't know if I'd start with that little, but you could if you want, because you can. There's an infinite amount of sample 1 for you, so you could basically use a liter of sample 1 if you wanted. Just keep pouring more and more and more in. You could use as much as you want. Although I don't know if there's a container that holds a liter. I'll have to see. I don't know if there is. Let's see. Oops. What's the biggest container? Oh, there's a 1,000 mil beaker. So you could probably put 500 mils in there and then add your silver to that if you wanted to. Then you get some big numbers. So any other questions?
I want to ask you why we have to know the density of the arsenic solution.
Because you need to calculate the mass of your original solution.
Mhm.
In order to give me in order to give a mass, you have to calculate what, from your sample 1, what's the mass of the sample. And then you're going to figure out what the mass of the arsenate is and divide it by the mass of the sample. And multiply that by 100. That gives the mass percent, or percent mass of arsenate. And in order to calculate the mass of the sample, you need, and you only have volume, right? You only have 50 mils. So you don't know what the density is. You don't know what the mass is of that. You need the density. And the density is 1.05 grams for every mil. So if I have 100 mils of sample, it weighs 105 grams. So 50 mils would be half of that, or 52.5 grams.
Okay, I have another question.
Mhm.
How you can answer the question for post-lab questions and error analysis question? How can
Mhm.
the answers?
Oh, look in the refer to the lab manual, because in the lab manual there's another similar type of experiment where you've got solids and you're measuring the mass of solids. And so basically, yeah. So read the lab manual. If you still don't get it, we can talk about it at office hours.
Okay.
Yeah, you'll definitely want to read. That's one of the things to look at. I don't know if I gave you the page to look at or not. If not, I will link it in Canvas. But yeah, it's a reaction. It's one in Canvas.
Professor, I have a question.
Yeah.
How do in the table? How do we get the 1 m AgNO3 in ml?
That's how much. So this, let me clear this again. That is just how much of this you added. So this sample contains my arsenate. This sample contains my silver ions. So in the table, you're going to write how many mils of this solution did I add to precipitate all of the arsenate. So when you pour in 2 mils, you're going to report at 2 mils of that, my mass, this is how much of precipitate was formed, and the precipitate being this. At 3.5 mils, I got a different amount. At 5 mils, I got a different amount. And eventually, you will get the amount of product will stop increasing. And then you'll know you're finished. But yeah, the volume of the silver nitrate is how much you decide to add. That's where that volume comes from.
For that column, we put in the volume where it's finally precipitated.
No, for you, there'd be a separate line for each additional. So let's say for sample 1, you first added 1 mil, and then you got, it's like 0.005 grams of precipitate. At 2 mils, you got 0.01 grams, and at 3, you got 0.15 grams, and then you finally figure, okay, I'm going to add 10 mils. And you get 0.015 grams. Then you figure out, oh, that's all I'm going to get. That's the maximum. And then from that number, you figure out how much arsenate was there in the first place.
So you want us to report all of that into our data table?
Yes.
Okay.
Yep. But you won't calculate like the mass percentage of arsenate because you don't know what the final mass percentage of arsenate is till you figure out till you've precipitated all of the arsenate. So until you've precipitated all of it, you can't calculate that. So those will remain blank until you reach the maximum mass of precipitate. Only then do you calculate what's the mass percentage.
So
Okay.
if
Oh, go ahead.
So if 2 isn't the max of the precipitation, I will put 3, or not 10, 3.
Oh, right. Then yeah, whatever it is. So if it's once you get to the maximum, yeah, you only need to do that calculation once. The mass percent of just do that once, and you can do it in the next to 3, or you can do it next to 10. It doesn't really matter. But you have to prove that that's the maximum amount of precipitate you're going to get. So if you just dump the whole thing of silver in there, I mean, that's, you could do that, but what I'd rather you add a little bit at a time so you can see that the precipitate, the amount of precipitate increases until it gets to a maximum. Okay, any other questions? Okay, remember, I will have office hours tomorrow at 10:30. It's up on Canvas, the link. It's regularly scheduled, so hopefully there won't be any more problems like that. So if there aren't any more, oh, I see a flashing. Is there something on the, oh yeah, I forgot to ask if there's someone checking the chat. Is there a question on the chat?
Yes.
Okay.
So would we put 3 ml because that is already the max? Is that right?
So what I would do is, let's come back to the, oh, damn it. Okay, here's my data table. So what I would do is I would put, where's my drawing? Here we go. Yeah, so I would put, let's say I had 50 mils of sample 1. I added 1 mil of silver, and my mass was 0.01 grams. Then I had 50 mils. I added another mil, so my total's now 2, and I got twice as much. And I would just continue doing that until I'm done. So sample, this is just an example. I expect you to make your own data tables. So if you do 5 additions of 1 molar silver nitrate till you get to the maximum, then I want you to have that many in your data table. So just keep going until this no longer increases. So let's say, 3, and then 5, and then, okay, that's the most I'm getting. Now tell me how many moles,
Yeah, no, I know.
what's the
everything's
mass,
gonna be
what's
okay.
the
I'm
mass
not too
percent,
worried.
okay?
Oh, okay. But do we still have to get the mass percent of every single one?
No, because that will be inaccurate.
So only the
Because you don't know what the mass percentage of the original is until you've precipitated all of it.
So for the table, like all it will be given the information except the moles of ASO4, and I mean the three last part of the table, this is the one I have to calculate, but the first three, it will be given in the
Yeah, this this is from the experiment. This is from the experiment. This is from the experiment, and then these three you have to calculate yourself. Yeah. So you can calculate moles, you can calculate mass, but you cannot calculate mass percent until all of the arsenate is precipitated.
Okay, and for me, just to choose, no matter how much I choose, like if each student has a different amount.
Laptop.
Sorry, I couldn't hear that.
I said I have I have the option to choose how much I put the solution.
Yeah, you can add as much or as little sample 1 and 2 as you want.
Okay, I mean, it doesn't matter to be like similar to all students, all the same.
No, add whatever you want. The thing is, hopefully you're all gonna get the same mass percent.
Okay.
Because sample 1 and sample 2, I'm pretty sure should be the same for everybody. So no matter how much you use, the mass percent will be the same.
Okay, question. The percentage of mass for each table, it should be similar, just to make sure that
Yep. Yeah, yours should be the same as everybody else's, no matter how much volume of sample 1 you chose to use.
No,
The moles will be different, the mass will be different, but the mass percent will be the same.
If you want, up to you.
Okay, anything else before we wrap it up? I got dogs dead desperate to get outside. All right, I will see you 4:15. I'll see you then. So if anybody has any questions, this is a rather involved lab. There's a lot of calculations to do. Send me an email. Come to office hours tomorrow, or whenever you like. Or if you want to set up a meeting on your own, just let me know, and we can set up a one-on-one. Okay? All right. Stay well, everybody, and we'll see you in a
Thank you,
little while.
Professor.
All right.
Thank
Thank
you.
you, guys.